Okay, so if you want to divide it and find the number of factors, for 504, it would be like a lot. So instead, we have this like really useful formula. Or so let's consider this formula right here. Then the exponents are e1, e2, e3, all the way to ek. And the number of divisors is equal to e1 plus 1 times e2 plus 1 times e3 plus 1 dot 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 all the way to times ek plus 1. Does that make sense? Okay, so we can also like do this with this number. So we have 2 to the third times 3 squared times 7. So the number of divisors would be 3 plus 1 times 2 plus 1 times, and this is 7 to the 1, so it's 1 plus 1. And this is 4 times 3 times 2, which is 24. Does that make sense? Okay, does anybody know the proof, like why this works, or have an idea of how it works? Okay, I guess someone can write it in the chat, or like, actually, I'll explain it as well. So, okay, so the idea, it's more of a combinatorics or like combo argument, more than a number theory one, but we're still going to cover it here. So since we have this, let's consider choosing the exponent for each prime. So for example, let's choose the exponent for p1. It can be raised to the power of 0, 1, 2, all the way to e1. And this, they're e1 plus 1 numbers. Does that part make sense? Yeah. So Ryan is like explaining it in the chat. So we have this many ways to choose the exponent for e1. Okay. So let's consider 504 again. So 504 is 2 to the 3 times 3 squared times 7. Let's say we're trying to create a factor. Then the exponent that it has for 2 can be 2 to the 0, 2 to the 1, 2 to the 3, or 2 to the 2, or 2 to the 3. And we can continue this for 3 and 7. So it can be 3 to the 0, 3 to the 1, 3 to the 2. And for 7, it's 0 to the 1, or 7 to the 0 and 7 to the 1. So essentially the idea is to create a factor, we choose 1 out of these 4, 1 out of these 3, and 1 out of these 2. So that would make 4 times 3 times 2, which is 24. And this is also like the formula right here. So there's something that we're using that we're not actually mentioning or proving, but it's like really useful. And it seems easy, but it really isn't. So it's called the fundamental theorem of arithmetic. And this basically says each positive integer has a distinct prime factorization. So let me write it down. And the proof of this is like way beyond the level of this class. So it's something interesting to think about. Like why would each number have to have a distinct prime factorization? And for those that are interested, and you can like think about it, it's using strong induction, which is a technique that we're probably not going to cover in this class. Okay, so one last concept we're going to cover before looking at problems is called Legendre's formula. So this is a concept that like appears in AMC8s and math counts a lot. Yeah, that is what it says. Okay, so this appears in AMC8 and math counts a lot, but if you search it up, the notation is like really confusing and it's hard to follow. So basically what it does, given a prime p and a positive integer n, it finds how many powers of p are in n. So this is like kind of confusing. So basically consider like n equals 4. Oh, also factorial. So 4 factorial is 4 times 3 times 2 plus 1. And in general, n factorial is n times n minus 1 times n minus 2 dot 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 times 2 times 1. Does everybody understand like factorials? Like the definition? Okay. Yeah, you just multiply until you get 1. So let's consider 4 factorial. 4 factorial, it's pretty easy to compute this. 4 times 3 times 2 plus 1, it's equal to 24. So let's prime factorize 24. So it's 2 times 12, and 12 is 2 times 6. So this is 2 times 3. Yeah, Ryan said it. It's 24 is 2 to the third times 3. Does this make sense to everybody? Okay. So let the prime be be 2. So p equals 2. How many the number of like factors, or not factors, like powers of 2 that are in 24, here it's 3. Does that make sense? So basically that means 2 to the 3 divides 24, but 2 to the 4 does not. So do you understand like what Legendre's formula finds? I guess as another example, let's look at p equals 3. And these are both for n equals 4. This is 3 to the 1. So Legendre's formula should return 1. Because this means 3 to the 1 divides 24. But this means divide, by the way. 3 to the 2 does not. Okay. So this is what Legendre's formula tries to find. So now we'll like provide a technique to finding it without using the sum notation and like all those complicated things. So let's take as an example 6 factorial and 2. We want to find how many factors or how many powers of 2 are in 6 factorial. And with this case, it's technically possible just to compute it, and it isn't too difficult. However, there's a much simpler way to do it. So we look at what 6 factorial means. Times 5. Which of these 6 numbers, so which of these 6 numbers like contributes a factor of 2? Yeah. It's 6, 4, and 2 that contribute factors of 2. So we can essentially just ignore 1, 3, and 5. So now one might just think that it's 3. But Hansen already said that it's 4. So why is this? Yeah, Aiden said it's because of the 4. So it's because 4 is 2 squared. So this actually contributes 2 factors, or 2 powers of 2 to this. So now, okay. So this contributes 1, 2 to the 1, and this also contributes 1. So overall, it's 1 plus 2 plus 1 equals 4. However, Legendre's formula basically says this is equal to, so let's write out like 6. Let's divide by 2. Then we get 3. And this is dividing by 2. And then we write 3 here. And we divide by 2 again. And we get 1.5. However, now we just ignore the 0.5. So we have 1. Then we divide by 2 one more time. So this is 0. And after that, all of the values are going to be 0. So now we just add these up. And we get 4. So we can use this for for bigger numbers as well. So like, let's say we have 21 factorial, or let's say 29 factorial. And powers of 3. So how would we find the number of powers of 3 that are in 29 factorial? So we just like apply this formula, I guess. So we start off with 29 and we divide by 3. And we get 7 with a remainder of 2. But we can just ignore the 2. Now 7, we divide by 3 again. We get 2 with a remainder of 1, but we ignore that. And we have 2 here. And we get 0 remainder 2. And everything after is 0. So we add these numbers together. And it's equal to 7 plus 2 plus 0 equals 9. So you might be wondering, like, why does this actually work? Because I basically just gave you a technique and like said it works. But let's consider what it's actually counting. So the 7's here. It's counting 3, 6, 9, 12, all the way to... Wait, actually, I can't divide. Wait, this is a 9, sorry. All right. Sorry, this is 9. Wait. Yeah, this is 9 with a remainder of 2. And then we put 9 here. This is 3, 3 and 1. All right, sorry about that. So this is 3 remainder 0. And this is 1 remainder 0. Okay. So basically what this is counting is 3, 6, 9, 12, all the way to 27. Uh, 13. Okay. So this is counting them each once. But as we saw before, there are ones that are that we need to count again. So this counts 9, 18, 27 again. But then here with this 1, we can see that 27 is 3 cubed. That means it contributes 3 powers of 3. So we have to count that one last time. So that's essentially what it's doing. And one of the most important aspects, or like one of the most important things that you could do with Legendre's formula is the number of zeros in a number. In the end. So let's consider the problem where we consider 26 factorial. How many zeros are in the end of 26 factorial? So like, how would we do it? Wait, Aiden said, okay, yeah. Okay, Hansen said 5 and 2. So basically, consider the number of fives and twos. Yeah, and Aiden said there are a lot of twos. So essentially, to create a zero in the end of a number, we need 5 times 2, which is 10. Oh, wait, I can't. Okay, which is 10. So as Hansen said, only consider 5. Yeah, so we only have to consider fives. So essentially, we want to find how many powers of 5 are in 26. So we just use Legendre's formula. And we divide by 5. We get 5. Divide by 5 again, we get 1. Does this make sense? Yeah, so you add these together. And this is remainder 1, remainder 0. So it's just 5 plus 1 equals 6. Okay, so now I'm going to give a problem, and let's see how quickly you can solve it. So the problem is how many, or the first one to say the right answer in the chat wins. But I don't know what they win. Find the smallest possible n such that n factorial ends in 2020 zeros. Okay, so that's the problem. Yeah, you get bragging rights. And this is like, it's gonna require a decent amount of like guess and check, but also you can find it more quickly through like a trick. Oh, okay. So basically, oh wait, yeah, okay. So I don't think it's 100,100 because the question is like n factorial ends in 2020 zeros. Wait, is that the end? I don't think that's the answer because there are repeats of 5. Okay, wait, Anita. So basically, consider like 5 factorial. So this is 5 times 4 times 3 times 2 times 1, which is 120. So this ends in 1 0. So you want to find the number that ends in 2020 zeros. Um, wait, so what answers have the 5570? So it's like, I'll give you a hint, like test 8080. This problem's like actually kind of annoying. So I'll just say the answer is 8095. So there's a pretty quick way to find this, but I'll just show you why this has 2020 zeros. So we start with 8095, and then we divide by 5, and this is just like Legendre's. Yeah, I'll explain the fast solution in an email later. So if we divide this, we get 1619. And let's just continue like doing the formula. So we put this here, we divide by 5 again, and this is 323 remainder 4. So we take this out. So this is 323 divided by 5. This is 64 remainder 3. And we just keep doing this. 8 remainder 4. This is 1 remainder 3. So now we add these numbers together. And I think this, wait, I can't add. Wait, basically these are supposed to add up to 2020. Oh wait, it's because here, sorry. Okay. So this is 16. Oh yeah, this is 16. And we divide by 5 one last time. This is 3. And now, okay, so the sum is 2020. So I'll give a solution really quick that's like faster. Okay, yeah. Oh wait, I messed up again. Okay, sorry. This is 12. Apparently I can't do like division. Okay, so this adds up to 2020. So a faster solution is that notice that consider a number n. And let's say it fits this. And this is somewhat advanced. So don't be like discouraged or like sad because you can't understand it. So the idea is that there are approximately n over 5 that have 1. And this is approximately. And then there are approximately n over 25 that have 2. So this keeps on going. So wait, let's please don't spam chat. So you would get n over 5 plus n over 25 plus n over 125, and realize this is an approximation. Dot, dot, dot. And we're going to cover this 0, or we're going to cover this later, but this is equal to n over 4. And this is like an approximation as well. So this tells us to test 2020 times 4 equals 880. And we find that it's 3 less because of the approximation. So we simply increase by 15. Wait, please stop spamming. And this is like, does anybody understand this? Because this is a little like complicated. Okay. Yeah, it's just like an interesting idea. Okay, so now we're gonna go a little bit easier and cover divisibility rules. So who knows divisibility rules? Like for 2, 3, 5, 4, 5, all the way to like, I guess 11. Okay. So I guess we're just going to go through all of them. So for 2, yeah, it's just even. Okay. So this is even, and an easy way is last digit and if you're confused about any of these, just ask in the chat. Like you can, it's like useful to memorize these, but don't like just read through them until you memorize them. Do it so like do problems so that it like makes sense. So 3, the sum of the digits is divisible by 3. We're gonna provide a proof of this next class. Okay, so 4, last 2 digits. For 5, last digit is 0 or 5. 6, divisible by 2 and 3. So we can just look at these two rules. Yeah, as Eric says, the best way to memorize something is to understand why it's true. Okay. For 7, there is a rule, but it's like kind of bad. So the rule, you take a number. For example, let's say we have 5, 3, 7, 2, 4. If 7 divides this number, then 7 divides 5, 3, 7, 2 minus 2 times 4. Yeah, Logan said this. So this isn't that useful, but yeah, it's kind of bad. So this isn't very useful, and a lot of the time, it's just faster to divide 7. For 8, last 3 digits are divisible by 8. For 9, the sum of digits is divisible by 9. Yeah, we're gonna provide a proof for 3, 9, and 11 later. Wait, Eric, can you type the 7 into the chat? Because I don't know any other rule. So for 10, the last digit is 0. And for 11, the alternating sum is divisible by 11. So basically consider like 5, 2, 9, 4, 2. Okay. So the alternating sum is 5 minus 2 plus 9 minus 4 plus 2. And this is equal to 10, I think. Yeah, it's equal to 10. And this is not divisible by 11. So 11 does not divide 10. So that means 11 does not divide 5, 2, 9, 4, 2. Okay, do these rules make sense to everybody? Are there any that that you want explained again or something like that? Wait, the pyramid thing? I'm not sure I know what the pyramid thing is, but I think it should be similar. Okay, 8. For 8, the last 3 digits is divisible by 8. Yeah. So for example, let's say you have 4, 2, 5, 3, 6, 4, 0. So in order for this to be divisible by 8, we just ignore all the digits except the last 3. So we just these don't really matter. We'll provide an explanation for this in the next class. But basically 8 divides 640. And this is easier to check. Oh wait, yeah, that's a good question. So this is easier to check. But what if there's only 2 digits? Let's say the number is 56. Then you just divide. Wait, Eric posted one for 7, but it looks complicated. So I think 7, the easiest thing to do is just divide by 7. Okay, so did these make sense to everybody? Oh, okay. Do you want to explain 11 again? Wait, Chloe asked to explain 11. Okay, so I said it's the alternating sum. So let's say you have a number let's say 5, 3, 4. I'm just saying random numbers. 2, 4, 3. So one of the I guess another way to explain this is you take the sum of every other number. So let's add these 5, 4, 2, 3. This is equal to 14. And now let's take these numbers 3, 9, and 4. So 3 plus 9 plus 4 is equal to 16. So basically the formula is that the difference, these have a difference of 2. And 2 is not divisible by 11. So that means 11 does not divide 5, 3, 4, 9, 2, 4, 3. Does this make sense? Adam, the one for 6 is that it's divisible by 2 and 3. Okay. So now we're going to go over a few problems. I have them here. All right. This is the first problem. Just, you guys can work through them by yourselves. And I think they're going to be increasing difficulty.
Wait, what was the 9 divisibility rule again? I forgot.
9. I won't move this, but the sum of the digits is divisible by 9. Okay, yeah. Ryan and Eric and another person said the answer. So what's the first thing you do for this problem? Okay, yeah. Hanson said find u. So first step you want to find u. So the way to do this is you remember the divisibility rule. So it's 2 plus 0 plus 1 plus 9, 8. It's too thick. Okay. Plus u is divisible by 9. And you're given this. So you realize that these add to 11. So u plus 11 is divisible by 9. So factors of 9 around this are just u plus 11 equals 18, which implies u equals 7. Okay, so this, we found u now. So the next step is we want to find the remainder when it's divided by 8. So when 20187 divided by 8. Yeah, so once again, to simplify the calculations, we just consider the last 3 numbers. And this holds for like remainder as well. Yeah, that's what David said as well. So 187 are the important ones. So now we just divide. So this is 2, this is 3, 24, 3. So the remainder is 3. So the answer is 3. Okay. Does this make sense to everybody? Okay. This problem is just kind of annoying, but you can try it out. This was a AMC 8 number 18.
No.
But like with the formulas provided, it isn't that difficult. Wait, Eric said 4729. I think that's a bit too high. Are you sure about that? Yeah, Ryan is right. So I guess I'll give a bit more time. Oh wait, Ryan, so you want to explain how you did it? Okay, so Ryan basically just prime factorized it very quickly. So let's just like draw a tree because we're not that fast. All right, so this is, wait one sec. Okay, so this is equal to 11616, and we do it again. So this is 2, 5808. We divide again, 2904. We divide again, 1452. And again, so this is 726. And let's like put this up here so we don't run out of room. So 726, we divide again until we ran out of 2's. So now we divide by 3. This is 3 times 121. And using the divisibility rules, you can recognize that this is 11 squared, or you can recognize that this is divisible by 11, or you just remember that this is actually 11 squared. So this is 11 times 11. And that means 23232 is 2 to the 5. Wait, no, I can't count. All right. 2 to the 6 times 3 times 11. Wait, did I mess up? Where did I mess up? Oh, wait, I didn't mess up. Okay. So this is 2 to the 6 times 3 times 11 squared. So this is, using the formula from before, this is 6 plus 1 times, the number of divisors is 6 plus 1 times 3 plus 1 plus 2 plus 1. which is 7 times 4 times 3, which is, wait, what? Never mind, I'm bad. Times 1 plus 1 plus 1, which is 42. And that's the answer. All right, so one of the most important things with this question is like speed. So when you see this question, you should immediately think of prime factorization. So immediately you want to prime factorize it, and you might screw up a bit and like make arithmetic errors like me. But a big part of the AMC8 in math counts is just like being fast. Because in AMC8 you get 40 minutes, and math counts I think you get 40 minutes as well. And that's for a lot of questions. So you want to get through the questions as quickly as you can while also being accurate. So for this question, it isn't actually too difficult, like the concepts required, but it could be a really annoying like time drain if you mess up a lot of times. All right, so we have this question. Yeah, the AMC8, you always, a lot of the time, unless you're like pretty confident in getting a really high score, then you end up having to guess. Also, a tip is guessing C. Well, yeah, 17 is pretty good, especially because you're not like that wasn't your eighth grade year. Yeah, it was 212. Okay, so this is just so those we were like pretty fast. So this is just Legendre's from what we had before. So we look at factors of 2 and 5. And there are a lot more factors of 5, so we focus on that one. Yeah, so we just look at factors of 5. So we divide by 5, and we get 171 with remainder 3. So we just ignore that. And everybody, we just like continue doing this. This is 34. Remainder, wait, yeah, 34, remainder 1. We take this out. We divide by 5 again. This is 6, remainder 4. And one last time, this is 1, remainder 1. So now we have these numbers, and we add them up. Wait, acronym? Okay, we add these up, and we get 212. And that's the answer. The way you write this out is Legendre's formula. You can search it up, and you get like summations and floors, which is essentially what we're doing here, but written out like, well, Wolfram Alpha. Yeah, Wolfram Alpha can find this in a few seconds, or like 1 second. Okay, this is another problem. You can try it. People have said C and B, but I don't think those are the answers. Oh, yeah, I did say a tip was to guess C, but like, um, probably try solving it first. Yeah, people have said the answer, but I want like more people to figure it out first. Yes, someone is correct. It's D. So if you got C, you might have been making like some. Yeah, people are getting D now. So if you got B or C, which is the other ones people got, you were either guessing or you made like some small errors. So what's the first thing we do when we see like this big factor? We can't just use Legendre's immediately. So what do we do? Yeah, Ryan said to simplify to that. And Aiden said to factor. Yeah. So this 98 factorial plus 99 factorial. This is 98 factorial times 1 plus 99 plus times 100 plus, wait, never mind, one sec. Okay, 1 plus 99 plus 99 times 100. Okay, so we'll do Legendre's later. So let's simplify this value into parentheses first. So this is 98 factorial times 100 plus 98 times 99 plus 100. And this is times 100 times 100. Just by factoring this again. By factoring this again, we get okay. So we can quickly find the number of fives in the second part right here. So 100 times 100 is 2 to the 4 times 5 to the 4. So this 4, this gives 4. So now we want to find the number of powers of 5 that are in 98 factorial. So with 98 factorial, this is 19 remainder 3. And then we divide again. We take out the remainder 3. Yeah, we used Legendre's on 98. So this is 3 remainder 4. So this is 19 plus 3 is 22. So we have 22 and 24. So now we add them together to get 26. Okay, does this make sense? I don't think this was B. Yeah, this was D. Okay. This is the last problem. It's from an AMC 10 and it's number 14. So it should be a little bit more difficult. There are a few of you that might have taken this test, but I'm not sure. Wait, there are no answer choices. So if you put C, then like that's kind of sus. Wait, can you not like reset chat or like spam? Oh, it was the first AMC that he took. That's 29. Oh, okay. Yes, it is. One sec. Yeah, it was 12. For the other people who haven't taken this test, I'll give a bit of time to try it out. And I'll just explain in the last like 5 minutes. We might go over a little bit. Okay, I'll do this. So first, the first thing we try to do is we look at these numbers. We notice that 19 factorial, using Legendre's with the prime as 5, we get 19 to 3. And since 3 is less than 5, oh yeah, so we have 3, it ends with 3 zeros. So this immediately suggests that h is equal to 0. So this is the first like observation that we make. And actually in the real test, I didn't make this observation. So I ended up guessing it, or like I simplified it down and then I guessed it. And I guessed it right. Okay. Wait, someone just joined. All right. So now something that's useful, we notice that it's sum of digits. So this suggests to take 9, or consider p equals 9. So wait, it's okay. Just ignore that. So p equals 9, and with Legendre's again, we get 2. So there are 2 factors of 9 in 19. So clearly, that means 9 divides 19 factorial. So now we use divisibility rules. So the sum of the digits is divisible by 9. So 1 plus 2 plus 1 plus 6. This is just kind of annoying to compute. We find, wait, let's calculate this. So this is 410. So this is 33 plus t plus h. 9 divides this. Does this make sense? Oh wait, I missed. Oh, sorry. This is t plus m. Does this make sense? This is just like adding them all together. And if we add these together and simplify, this is 33 plus t plus m. Okay. So if some people are confused right now. So essentially what we did, we noted 9 divides 19 factorial. So using the divisibility rules, 9 must divide the sum of the numbers. So this is all the numbers written out. And it turns out that 9 has to divide 33 plus t plus m. Okay. So this basically means that t plus m, well, written with like modular arithmetic, which we're going to cover next class, this means that t plus m, when it's divided by 9, leaves a remainder of 3. So here, t plus m can be 3, 12, 21, etc. Does this make sense? Except like all of them are impossible. Okay. So at this point, we realize that t plus m plus h is equal to either 3 or 12. 21 would be too high because h is equal to 0. So now we can already eliminate it down to 2 choices. On the actual AMC 10, this was a multiple choice test with A as 3, B as 8, C as 12, D as 14, and E as 17. So we can ignore these. And it's one of these answers. So already guessing is really optimal. But we can actually find the answer. Yeah, someone said C, and that was correct. Okay, so the way we eliminate down more is you note that 11 divides 915 factorial. So this means the alternating sum is divisible by 11. So since we don't have much time, I'll just give like, if you do the alternating sum, you find that t minus m minus 7 is divisible by 11. And you also know that t plus m is divisible, or written with mod notation, which we're going to explain next class. So don't worry if this is like a bit confusing. This is 3 mod 9. And t minus m is equal to 7 mod 11. No, there isn't any like assigned homework. But like a good source of problems is past AMC 8s and 10s. Also math counts if you want to get better. So it's pretty easy just to see that t equals 4, m equals 8 leads to the correct solution. So this could be done with like testing a bit, testing with like these values, and you find out that t equals 4, m equals 8. So this gives the answer of 8 plus 4 plus 0, which is 12. Okay, so I'm gonna end class soon, but just a few things. Are there a lot of good resources online to do math like between these classes? So if you have the AOPS books, you can work through them, especially like pre-algebra and like the introduction series. And on AOPS, you can work on Alchemist and Math Counts Trainer. And AOPS also has all the past tests, so you can use those. For the win, I guess for the win is good, but it's also like it's like fun, but you also won't get a lot better. So one last thing, I sent a survey in the email, so please fill it out, and we're gonna determine the next class and like the content on it based on that. Okay. So there's a survey in the email I sent yesterday. Yeah, don't troll. It's anonymous, by the way, but don't troll. Okay. It's about the difficulty of this class. Wait, Hanson, I didn't want to collect the emails so that it would be so people don't feel pressured to say something like false. Okay, so everybody can like leave now. Thanks for coming. Stay safe.
Thank you.
Thank you, teacher.
God bless our world.